message I put during Compass, like right in the middle. So I thought maybe if you had some homework questions, I could have done it remotely. But I kind of like doing that during Compass. I might, might do that if I remember. It's the same link all the time. It was my Meet link from last year. Okay, so remember, function, not a function. I hope you play with your friends. 1 over x is the first one that I draw here. Remember that this is where we have a horizontal asymptote and a vertical asymptote. So I just wanted to put this down so you remember this. Because you can't have 0 in the denominator. So that means x equals 0 is a vertical asymptote. And then our degrees, I guess I could put ASYs here, ASY. All right, the degree of the numerator is smaller than the denominator. That is why by default you have y equals 0 as a horizontal asymptote. And then this graph actually does look like this, behaving to the asymptote and behaving to the asymptote like this. I could plug in points. Input, say it. Output. It's kind of tough though. When I plug in 1, I do get 1, 1 comma 1. When I plug in -1, I do get -1. So those are interesting points. But notice when I plug in 2, 3, 4, 1/2, 1/3, 1/4, those are all getting 3, 2, 1 smaller. So small as I keep plugging it in, you almost get to, say it, 0. So that's why we have a horizontal asymptote there. Some things to know, by the way. But all we're playing is function, not a function. Is that a function, yes or no? Does it pass the vertical line test? So, and then here's one more thing. Is it a one-to-one function? Does it pass the horizontal line test? Ooh, not many people are talking. 1, 1, 1, 1. It is one-to-one. So I wanted to put some, more to that, make it more cat-like. Meow. All right, we should know 0 squared is 0, 1 squared is 1, -1 squared is -1. We should know instantaneously that this is a little parabola, a parabola. Sorry for my shakiness. Ooh, my old age. Okay. First of all, is that a function, yes or no? Yes. Is it one-to-one? No. And then we're going to break this down even further. This is why at the end, when we flip over the page on our last examples of the day, I put it all together. I have 2 examples where we're gonna do everything. Is it a function? What's the domain range? What's all the other stuff? All right, and then from the notes, this was this parabola. We had that as one of our examples. Well, this is what happens with a y-squared function or not a function. Not. So this is the function, not a function section. This is not a function, and we move on. Okay? So I wanted to synthesize your thoughts on that and then go to this next page. And I like how I did this. This was randomly perfect where each box fits right in my screen. All right? We don't need a really, really big coordinate plane for this. You don't have these, so just go. All right? And then here's what this is. This is a line. By golly, guys. 0 in for x, I get 0 for y. 1 in for x, I get 1 for y. -1 for x, I get -1. That is a line. There's a whole bunch of different functions. The majority of the functions, the domain is all real numbers. So this is domain range game. The majority of functions do not have a problem with what you plug in for x. Like this last example, number 2, or letter B. The domain is all real numbers of an x squared. You can square any number, all right? But this isn't even a function, so we don't care about domain range. This one has the domain range issue, so I think that's why I have it up here again. The range, when you analyze and look at the picture, you do have to be careful, but you have to watch the picture. The range is actually all real numbers as well. This is the majority of the time. When I go back, I'm sorry for still doing this, but just for thought, is the range all real numbers for this one? Yes or no? No. You've got to start thinking about the graphs and how the range is different. This is missing, so the range of this is 0 to infinity, 0 with a bracket on it. So the range is tough. You must look at a picture. I decided to pick this one. Input, say it. Square root of 0 is 0. You're going to have to do this a lot tomorrow. Tomorrow is a special day. Square root of -1, can't do it. Not in a real coordinate plane. Not on a real number line. So that's why it starts there. Square root of 1 is 1. Square root of 4 is 2. I don't know. I'm just doing real quick sketches here. Square root of 9 is 3. I could do this forever. Not that the square root of 8 doesn't exist. Square root of 8 is a decimal. All right, so, but we can square root any positive number and get an output value, and that's the picture. Well, now I did this on purpose. This is the first kind of function where we do have a limitation on the domain. So I gave the parent function square roots. And then when we start talking about transformations, which I'm going to kind of talk about that tomorrow, then the domain and range change, and you need to be aware of that. So that's what we got going on the next couple days. And then, of course, if you analyze the range, just by coincidence, it's also 0 to infinity. But look at the y-axis. 0 to infinity is covered by this picture, these y-coordinates. I don't understand why students have a hard time figuring out range from a picture. All right? And then this is special again. Same one, but I wanted to separate the ideas here. Now we're talking about what's the domain and range of this one. Well, if this is the picture, we have that vertical and horizontal interruption. And it just so happens they do have the same, x equals 0 and y equals 0 are the asymptotes. So in both cases, we've had a few of these where I had to write this annoyingly down. It is negative infinity to infinity for the domain, except for 0. And I like doing that this year. It's like a new idea that I've had. And that's the only way you can exclude 0. They're not related. The reason the range is what it is because of that horizontal asymptote, which I described how we get that last problem. And we'll have to have a little bit more practice on that as we go. I think the notes are pretty thorough about asymptotes Friday, and we're going to do another one that has asymptotes at the end on your back sheet of paper. Okay, this is something we've already had. I figured I'd synthesize those 4 words that I just threw at you. The first one is just, I kept jacking around with the space here. I don't think I need as much as I have here. Continuous, that's just like this picture. I don't know, you can make up anything. Anything that doesn't have an interruption. Vertical asymptotes are an interruption. That's our 4th one, letter D. Removable discontinuity. I guess I should call these discontinuities. Removable discontinuity. That's very simple. Same graph or similar, but there's a hole there. And you will see that in chapter 2. We will have graphs that have holes in them. There's a specific reason why that happens. So just for purposes of this, just tell yourself that's removable. It's almost continuous, except for that one little spot. And then if you read the book, they explain, they call this removable because you can just put a little patch there, like a pothole out on the streets. And then it would become a nice smooth street again. So that's why it's called removable. Okay, what's this one called? We go like this. Then maybe an open dot here, and then we have a closed dot here, and then it continues from there. What's that called, everybody? I would have to jump from this graph to this one. All right, so that's quite simply called a jump discontinuity. I'm just putting jump. I'm tired. You can put DISC. All right, and then the last one is a function that we've already had twice up there. Okay, but let's change the script a little bit here. Let's say we have this, and then a dotted line here, and then this. Really only care about the vertical interruption. There is, and I kind of made up a horizontal asymptote there as well. But, and let's say that's like at -1. That one's called an infinite discontinuity. So that classic. And then let's say this. Let's say that is -1. You would say an infinite discontinuity at x equals -1. That's how you would state that. I guess you would say that the jump discontinuity is at some x value as well, where you have to jump, the position where you'd have to jump from. Okay, so those are just words, all right? Very simple vocab words. They just have to be memorized. I don't let people say I don't get it on that. It's just it's a word, It's just like my name is Danny. I don't get it. What do you mean? That's my name. That's what I'm my label. That my parents forced upon me when I was born. Okay. Let's draw this. Wait, I wanted to see the picture that I had in the past here. So I used to do this on the board, and I actually took a screenshot of it. All right, yeah. So let's go at -3. So -3, 2. I did give you a graph for this, right? And then at 1 comma -4, let's do this. And then this. And then this. Oop, that didn't go. Sabotaged by the computer here. All right. So very simple on this. And you're asked to do this on certain functions. I'm going to ask you either on tomorrow or Thursday. I don't know where I want to get that worksheet that we're going to do. I think tomorrow I have a different activity. But what's my finger doing, or what's my graph doing from here to here? Increasing, decreasing, or constant? Come on. That's increasing because you read left to right. Remember, the word increasing is already describing the y. So I must name the x's, I must name the inputs that make the outputs increase. So this is describing the outputs. What are the inputs that make it happen? That's how I'm wording it with my my students in Math 2. So from the left, what number is way out there? 3, 2, 1, go. -infinity. All the way up to what x value? 3, 2, 1, tell me. -3. Never do you put brackets on this. Because at -3, that's where there's a change in direction. Actually, as a calculus concept, at -3, the graph is like in a millisecond constant. Right? Slope of a tangent line would be something used for that. Then it's doing what? What's that? 3, 2, 1? Decreasing. And that's from the x's that you plug in, from -3 to 1. This is why I made specific coordinates, so that you understand this must be the x coordinates that the inputs you list that creates the decreasing outputs. Oh, I don't know how else to explain that. And then I got green. That's constant, and that happens from 1 to infinity. So just the idea of labeling those increasing and decreasing behaviors. I thought that'd be a good idea to have that in that little section. Should not be a problem. It's actually something you've done over and over and over again. I'm working with Math 2ers and Math 3ers in there, so they know. All right, this is one that I don't think I covered with you. I think my coordinate planes are crooked. I did insert a line. I think they're slanted a little bit. I don't like that. That drives me crazy. Okay, but let's draw this. And then I have an example where we have to get to the calculator. We actually did this though on Friday. Remember I hit the max or min button? Right. Showed you that? Yes, Mr. Samuelis? Okay, thanks. Now, first of all, what's this? Is that a maximum or a minimum? 3, 2, 1, go. Okay, but is it absolutely the maximum value of this graph? Yes or no? 3, 2, 1? No. So this is why this is called a relative maximum, not absolute. Okay. Now I'm going to make up a coordinate. Let's say this is -2. Just go ahead and humor me on this, and this is 3. So it's a relative max at, oh wait, no, sorry, of 3 at x equals -2. This is how you word it. That's why I wanted to fit in this and kind of give some more space so that we could have that listed as such. You don't say the relative maximum is -2, 3. You say the relative maximum is 3. Again, the max is the y value. That's why it's called the max. And it's located at the input of x equals -2. And then, is this an absolute or relative? 3, 2, 1, go. Relative, because this goes lower. And it's a relative minimum. Same thing, and I think you get it. I'm just going to put relative minimum. And then we won't do the whole coordinate specific thing. because I didn't do any coordinates there. I hope you get that first part, how you word this, though. That's very important. Okay, then why do I have a second graph? Because I wanted one of these. What the? Nice roller coaster. Okay, here we go. Relative or absolute? 3, 2, 1, go. Relative, and it's a relative max. And then it would be the same thing at the y coordinate. I'm sorry, of the y coordinate at the x coordinate. What's this, relative or absolute? 3, 2, 1, go. Relative, because it goes forever down than those other arrows. This is a relative min, and we'll talk about that on a calculator, how to find those. And then this is why we do it. Come on, guys, this is relative or absolute. 3, 2, 1, go. This is an absolute maximum. This is the absolute highest of this graph. So that's the difference between relative and absolute. All right, hopefully you understand that. Like a way of thinking this English-wise, not to overdo it. Relatively speaking, that means in this just general area and not looking anywhere else, just looking right here, that relatively speaking is the maximum in that little area, not the whole graph, right? And that's what we got to do here. Okay, big star here. This is after I describe this, we're going to have to flip over to the next page, and I have some questions ready for this. You're going to have to do your notes on the back, okay? But I do like this here, so that this is the general thing, and I did do general basic, the beginning functions that are even and odd. And yes, there is a link here. What is the power on this, even or odd? Even, all right, but that doesn't mean that's only what even functions are. There are more, not just ones with even degree. Input, output. Here's what an even function has. And I guess I should have put this here. This one is even. And graphically, the graph for even functions is symmetric with respect to the y-axis 100%. Lock it in. And that's graphically what has to be true if it's said to be even. If a graph is not symmetric to the y-axis, then it is not even. Very simple. Here's what's not so simple, and I probably will ask you this on a test. Algebraically prove that this is even, odd, or neither. Those are the kind of questions that we have. Here is the algebraic test. If you plug in negative x for x, and the resulting is no change, you get the original function right back, then you're guaranteed the graph will be symmetric with the y-axis and therefore be even. So here's how it shakes out for this one. The test algebraically, I plug in negative x for x. This is how it has to be plugged in, folks. You're inserting a negative x for x. So that is how it's going to look. By the way, everyone, what's a negative squared? 3, 2, 1, positive. Notice when I plug in negative x for x, I get exactly what I started with. Since that is the case, then you have an even function, and that's the work that proves it. So I tried to simplify this as much as possible, so you have this little section in front of all the other 9, or with the other 9, that you can remember the algebraic test for this and do well with it. Okay, by the way, input, say it. Input 0, I get 0. Input 1, I get 1. Input 2, now you want to get nuts? Let's get nuts. It's starting to go crazy. It goes way up here, 2, 8. I plug in negative 1, I do get negative 1. Oh. I plug in negative 2, I do get negative 8. Ah, this is what the graph looks like. By the way, just for giggles, what's the domain? 3, 2, 1, 0. Or you could say all. Anyone? Let's do that on the second one. What's the range? range. 3, 2, 1. I just gave the answer. All real numbers. You look at this, and all the y's are covered. Y. All right, next. Guess what the symmetry is? Here's my symmetry sound. Look at that. There's symmetry. What did I go over? Where did I pass over to get those connected points through symmetry? Starts with an O. Origin. Okay, so graphically, odd functions, I don't know why I changed to blue, are symmetric about the origin. I'm writing like a cave person here. Sim about origin. Okay? So that's all we need to understand there. Here's the algebraic test. If I plug in negative x for x, what ends up happening? Well, let's fill this in later. So what's f of negative x? I plug in negative x for x in x cubed. Hey everybody, what's a negative to the third power? A negative. So what happened when I plugged in negative x for x? I ended up with the exact opposite function. And there it is. There's the algebraic test for origin symmetry / odd functions. Okay, so it's different. Negative x for x, no change, even. Negative x for x, completely opposite, odd. Opposite odd for algebraic tests. Okay, and then the last two, 9's important, 8 isn't. I really don't like 8. I don't really care about this. This is the only book I've ever heard of boundedness, but it isn't hard. Okay, so I thought, for instance, one thing we could do is like one of the functions we had before, which was y equals 5 raised to the x. Remember when we had that and I took 5 to the 0 power, and that's 1. 5 to the first is 5. This is why this graph starts taking off, because 5 to powers really goes large, to second, third, fourth power. But then 5 to a small power, or a negative power, actually means 1/5. 5 to the negative second is 1/20. I'm already annoyed. I already know that this graph is never, ever, ever going to hit 0. I don't care what I raise 5 to as far as a negative power. It's always going to be 1/5 to a positive power, getting closer and closer and closer. So there is no more graph underneath this. That means this is bounded below. It has a boundary. That's all boundedness is. And you did not see this yet. This is why I'm just throwing this in as an afterthought. Just let's get over it. Even an odd was new too as well. So, but I just wanted to make sure that you knew what it was. And not many things are bounded above or below. But that's one of them. And then say you had a picture like this. I at least hope that you know that this picture, those are what's when I draw that dotted line. 3, 2, 1, go. Let's start that again. What are those dotted lines? 3, 2, 1, go. Asymptote. So you at least know that we have a boundary above and below. Here's what you just call this. This is absolutely bounded. When you're bounded both above and below, you say bounded, period. If you said bounded both above and below, I'd be okay with it. I wouldn't be mad at you. All right? But that's what boundaries are. If you have something that has, you know, and there's nothing above it, I can't really think of a function right now except maybe an upside down exponential function. Sorry, I couldn't think of the word. But that's just really what it is. Not many things are bounded. Question? Oh, don't worry about that. Why is it bounded below? There's a boundary below. It's like think of like a fence, like an electrical fence. That's a boundary. I can't get past it. You know what I mean? Got it? So that's the best way to think about it. All right? And then end behavior. I had a couple things that I wanted to show for this. And we need to remember our limit notation. You ready? All right? Stretching, huh? You want to pull a math muscle. Okay, let's do this little thing. Let's do the classic x to the third. I use that in our continuous little things. Okay, and then let's do like this is not an asymptote, but I'm trying to separate these two, so these are completely separate. Here's what an end behavior. Hopefully you remember this, and you did do this. I know you don't like hearing that, but you did. You've seen this before. What's LIM stand for? What word for math? Lim. There's only two more letters. Lim. It. And that's actually limit notation to describe end behavior. And then on the bottom for this first one, we're going to put X arrow infinity. And then we're just calling this graph f of x. This reads, I'm not writing this down because this is not the first time you're seeing it, but I'm teaching it like it is the first time. I'm just not writing everything. This really means as x approaches infinity, what is the limit of y, or what does y approach? That's all that it says right there. So as I plug in big numbers for x, where do the y's go? And then I always use my xy finger here. Right now we're at 0 for this x comma y, whatever. This is like 5 comma 0. But as I move out to infinity for x, where does my y finger go? Where's my y finger going? Where's it going? Up to what number? Infinity. So that is as simple as I can make it, getting these correct. Whenever I do the chapter 1 test, this is a disaster, and I don't understand why. Input, output is all we have to think about. These are not points that we should be missing, not even remotely. All right, and that's where I just have to, draw a line in the sand and say, boy, you guys should not be missing these kind of questions. First of all, you've seen this notation, and second of all, even if you haven't, I can't explain this any better. X finger, Y finger. Fine, let's go like right here. It doesn't matter in the middle. This is end behavior. What happens at the ends, not in the middle. All right? So X finger, Y finger, and then as this X finger goes out, here goes my Y finger. X comma Y, input, output, input, output. What happens to the outputs as I plug in these inputs? Where do they go? Negative infinity. Should not be missing these. Not at all. Okay, but then that gets more special. Let's draw a horizontal line. Horizontal asymptote. Let's say that's at y equals 2. And then let's make a vertical asymptote. You will do some behavior on this vertical asymptote. I'm not even going to number it, though, because it has nothing to do with this question. And then do this. Draw our classic rational function thing. Okay, now we got a problem. We got a difference. End behavior asymptotes are always limits where x approaches infinity or negative infinity. So draw it again. And I'm going to zoom in on this part because we got that part done. Makes it easier for me to write too. And then the limit as x approaches negative infinity of f of x. X finger, y finger. Oh, I forgot to go to even and odd. Darn it. Sorry for almost kicking your desk. I was supposed to say at 7, stop and go to the back of your notes, but we can reboot our minds. All right, so let's do this and finish it off. Here's my x. So x comma y. And I'll move so in case, let's move this picture so you can see me in action in class. Nice. Is the camera at about 15 pounds? Holy crap. I should probably start working out. Anyway, so x comma y, x comma y, x comma y, x comma y, 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 y. Where's y approaching? Not 0. 2. That boundary right there. Not bounded above or below. Don't think this is a bounded thing. Boundaries are the graph doesn't exist below a boundary. The graph does exist below that boundary, so it's not bounded at all. But as I go out to infinity for x, I'm getting closer and closer, but never hitting that asymptote y equals 2. So the y values, if you looked at the chart, get closer and closer to 2, but never make it to 2. So that is why that's end behavior. What do you think this answer is in 3, 2, 1, 0, go? 2 on the other side. Who said 2? Did you hear me yell 2 really loud? A little hint. All right, because x finger, y finger, same thing again. As I plug in these x values, this is what y is approaching. It's never getting past that horizontal asymptote. So it approaches 2. So those are a little bit different. All right, let's reboot our minds. I screwed up. I wanted to do some more even and odd with specific questions, and it is going to take some time, so you're going to have to fight through it. By the way, what's the first word in this class? Starts with a C. I didn't hear. Someone said something weird. It was college. I don't know what. I heard something different. College. You know, you're going to have to really focus on. And I really did, I think, a good job of trying to get you a synthesized piece of paper so that you can get all these terms. But, you know. All right, so look at what this says, and then go ahead and write that down. Tell whether each of the following functions is odd, even, or neither. That could very well happen. That ends up being neither. Then I'll zoom in on the first one that we have here that's right out of the book. So I guess you could just say it and look at the picture. I'm going to go ahead and prove it algebraically for each one of these. But if we look at this picture, you got to be careful on the picture as well. So you could go ahead and graph it. Does that graph look like it's symmetric with the y-axis? Yes or no? 3, 2, 1? Yes. But sometimes you could be off just by a micro hair, and it could be just off a little bit, so the graph could be deceptive. So here's the proof of it. When I plug in negative x for x, by the way, what is a negative squared, everybody? Positive. And then I notice that I end up exactly what I started with. So that is proof that this is even. This teacher, I think this was Westberg that made these notes. I don't often refer to the table. She also refers to the table and looks at 0, -3, and then sees the symmetry of these. When I plug in negative x, I get the opposite or the same y coordinates. And that's really what's going on with there. That's what this means right here. So this simple algebraic test will be needed on your upcoming quiz. I will ask you, even, odd, or neither, prove it algebraically. And you will have to have that written down. I'm just giving you the information, what I'm going to expect you to do. By the way, this is a quadratic. Is that symmetric with respect to the y-axis? Yes or no when you look at that picture? No, it's a little off. It's a little off to the side. So we already know no. Watch what happens when I plug in negative x for x. Sure, negative x squared is positive, but I have to plug in negative x here as well. And then what ends up happening is g of negative x looks like it's going to be about the same, but then a negative times a negative here is a positive. This is not even remotely the same thing as what's above there. There's a difference there. So what is it odd then? Did you get the opposite of what you started with? No, because these are the same, but only that term is opposite. So it's neither even or odd. And that will happen. Actually, very, very unique functions are even or odd. Most every function is neither. Just so you know that. And by the way, these are functions. They pass the vertical line test, so it's all good. What time do we get out of here? 12? I probably have time for, maybe I won't be able to do, the last couple. Maybe I could save that for the worksheet or maybe for bell work tomorrow. Because I feel like we still have had a mouthful. So always have some plan in place, and then we don't always get there. By the way, and because I do want to analyze this, all right, what are the vertical asymptotes? And it's the zeros of the denominator, which I think we've actually had. Did we have this exact one? I don't think so. And you can see it. You can see it in this picture. X equals 2 and negative 2 just for giggles. Is there a horizontal asymptote when the degree of the numerator is bigger? Yes or no? No. Another thing you got to remember. Look at the picture. There seems to be something though, but it's not behaving to a horizontal line. All right, so I look at that picture. Here we go. Here we go. Oh, take this little end. Take this little point right here. What kind of symmetry is that? About the what? What did I go across? Again, starts with an O. Origin. That means what kind of function is this? Odd. Here's the algebraic test for it to prove it. H of negative x equals negative x cubed. This is kind of, oh, wrong. That shouldn't be there. That should be here. Over 4 minus negative x squared. First of all, what's a negative squared? Looking at the bottom, what does this become? And you don't cancel these. I just yelled at my math tutors. PEMDAS. P-E, exponents. Then subtract S at the end of PEMDAS. So the bottom ends up being the same. The top ends up being negative. Now, if you look at this way, this is actually true. I could pull this negative out in front, and then this would be the same mathematically. What have I proved? I proved that when I plugged in negative x for x, I got the exact opposite function. All right? A negative in front of it. So that is the proof that this is odd. And that's why I wanted to take a moment to explain odd a little bit further. Mathematically being able to do those substitutions. The only one that really deserves a star out of all of these. And then, of course, the classic 1 over x. Let's just look at this and end it for the day because we've had a mouthful already. What does this end up being? The same, opposite, or neither? 3, 2, 1, go. All right, I'll start all over. You have one of 3 choices. Did I end up with the same function, the opposite of the function, or neither? That's your 3 choices. 3, 2, 1, go. Opposite. What does that mean this function is? Odd. This is an odd function, and then we're going to look at the picture that I actually started the whole day with. I think this was our first one that I looked at in function, not a function. There is a vertical asymptote. There is a horizontal asymptote, but there's certainly this symmetry. I'm going across the origin and seeing that there's a symmetric point across the origin that exists for each point. So that's also what odd looks like as a graph. Okay, I think you have enough information to do the remaining problems that I assigned in the book, and they are not lengthy. You may very well need your graphing calculator, but if we're doing even, odd, or neither, let's do those algebraic tests, all right, because that's what you're going to have to do on the test.